There, it's just so I don't trip and fall. Tonight, my name is Marty. I'm part of Chagrin Valley Astronomical Society. We're located in Huntsburg, and we consort with the library, the Park District Foundation, and Burton Library to present these programs once a month, and to also have the little telescopes you see in the back that you can check out free at any library in the county. Tonight we're going to talk about Saturn. Name Saturn comes from Saturnus, which is Latin, the god of wealth and agriculture. He was originally a Greek god, Cronus, not to be confused with Kronos, who is the personification of time. A god of agriculture, sowing and planting, early agriculture. Son of Gaia and Uranus. The Romans just dropped the O, and he's still called Uranus. Mother Earth and Father Sky. He was one of the Titans with his sister Rhea, who was also his consort. He fathered all the Olympians. The gods did that a lot. Little background, in case you're not familiar. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Easiest way to remember, my very eager mother just served us new pie. The one thing I remember from 4th grade. These are the planets to scale. Here's Earth. Here's Saturn. 98% of the planetary mass in the solar system is right here in these two planets. The gas giants. Uranus and Neptune are considered ice giants. They have heavier elements than hydrogen, predominantly in their atmosphere, mostly methane, which is why they're blue. Methane preferentially absorbs red light. So anything with a lot of methane is going to appear blue or bluish green. Rocky planets, not much there. Let me back up one. You see Saturn's at a 20-degree angle, just like the Earth. It has seasons. It goes around the sun at that angle. So half the time this is summer, the other half the time summer's down here. It has a 29.5-year orbit. A 1 year on Saturn is 29.5 years on Earth. Right now, if you look at it in a telescope, it'll look just about that angle there. It takes 15 years to go from all the rings on the top to the rings from the south. And then it just turns right around and goes back. And that's where we get our 29.5-year cycle. 1 Saturnian year is 29.5 Earth years. So this is 6 months on Saturn, 15 years on Earth. To give you an idea where we're at, here's present. 2024, 2025, the rings will be just about edge on. If you've never seen that, it's really cool. And it only happens every 15 years, so I've seen it 3 times. Yes. 2028 will be pretty much at our maximum tilt. Take a look at the inside of Saturn. There's 2 models. And no consensus on what's inside Saturn. The classic model, this is just a thin layer of gas, maybe a few thousand miles. And then there's enough weight and compression that it becomes liquid hydrogen. The helium, there's a little bit of helium in the atmosphere that will sink down and end up being a little ring around the core. And a rocky core, about 17 times the size of Earth. So it's tiny here, but compared to Earth, it's huge. The other model says that we still have our gaseous layer and the liquid hydrogen and helium, but the metallic hydrogen and helium it's about the consistency of gelatin. And with a molten inner core, the two would mix, because there's really nothing to keep them apart. So they would mix, you would have this molten blob somewhat in the center, but not necessarily centralized. it would be offset, indistinct edge, it will wobble around. Looking at gravitational attraction on the rings is how we come up with the fuzzy core model. Right now there's no consensus as to which one's right. So we look at Saturn, 54,000 kilometers at the poles, across the equator, 60,000. About a 10% increase across the equator. It's because Saturn spins fast, very fast. It has about a 10-hour day. The only one faster is Jupiter, who has an 8-hour day. I say about because it depends on where you're at. The equatorial zones and the polar zones rotate at 10 hours, 14 minutes at the cloud tops. The northern and southern temperate zones, 10 hours and 38 minutes. If we look at radar on the inside, the internal parts of Saturn by the core, we're getting anywhere from 10 hours and 32 minutes to 10 hours and 45 minutes. It varies. We're not sure why. So we try to come up with, I think it was 10 hours and 32 minutes is the standard we use for the rotation of Saturn. Saturnian year, 29 and a half. There's 24,491 days in the Saturnian year because it's spinning so fast. Every 10 hours over 29 and a half Earth years. The atmosphere, the light areas are called zones. The dark areas are called belts. These are cloud tops, just like you see on Jupiter. But they're a lot fuzzier because one, they're farther away. Two, there's not as much mass here. And three, there's some methane involved in the cloud tops, and it just makes haze. Atmospheric composition, 96% hydrogen. Molecular hydrogen, not atomic hydrogen. That's why it's H2. 3% helium. And then trace amounts, methane, ammonia, ammonium something. I apologize for not remembering that. Ammonium hydrosulfide. That's what it is. That's at the surface. These are the ices. This is what you're seeing as ices. The gases, they're pretty much, underneath the ice and transparent. Where you see a bluish tint is generally where we're seeing down into the planet. The darker it is, the deeper you're seeing in. The very light are ammonia clouds. Here you see some water, ice, ammonium hydrosulfide, and then these areas are mixed. Where you see that blue and the blue back here, you're looking down into the liquid hydrogen and helium. Great white spot. Saturn has weather, a lot of weather. This is similar to the great red spot on Jupiter, except Jupiter's is pretty much stationary on that one belt, and it's lasted for 300 years that we know of. These come and go, average once a year. That's about the size of the Earth. As it goes on, you can see here's the tail, so it ends up circumventing the whole planet. At that latitude, it's about 186,000 miles long. And it'll eventually widen out. And here it's about 9,000 miles wide. It's slowly drifting west, maybe 60 miles an hour, which on that planet is pretty slow. That's how big it is compared to Earth. You could set the whole Earth right there. The white is ammonia, mostly ammonia clouds. What they've noticed is a lack of acetylene. There's trace elements in Saturn's atmosphere, methane, ethane, phosgene, acetylene, hydrocarbons. And they notice when this first pops up, that this is mostly ammonia, but a surprising lack of that little bit of acetylene. We're not sure why. One thing you'll find is astronomers aren't afraid to say what we don't know. It's easier to stay out of trouble that way. It also has, right along the northern hemisphere, little white spots. Those are storms. They generally pop up in the summer. They'll end up ringing around the planet, and then come fall, about 7 years later, they slowly dissipate and disappear. We also have the dragons, what's called the dragon storm, because it looks like a dragon. That's just a big thunderstorm about the size of the Earth. What's odd about this is at night, it has almost nonstop lightning. And we don't see it, but we can detect it. When Cassini was there, the spacecraft orbiting Saturn, it could detect the electromagnetic transmissions from the lightning. The same way you get static a lot of times on an AM radio from lightning. And all night long, it's almost nonstop. When this gets into the daytime, the lightning just quits, just like flipping a switch. And then at night, once this gets into the shadow, the lightning starts kicking up. No idea why. But it keeps us guessing. Here's the North Pole, the hexagon, the polar hexagon, here, the polar vortex. This is a little hurricane right there. Little being a relative term. Here we go again. You know, you can fit Earth, 2 of them in there. What's interesting about this is the vortex is spinning this way, 300 miles an hour. This belt of Saturn is going this way about 350 miles an hour. And what happens, it sets up little vortexes all the way around that spin and maintain that shape. It looks pretty bizarre, but we're able to replicate that in a laboratory. And depending on the speed, you can get anywhere from 3 to 9 sides to your little polygon there. But this area right here doesn't move at all. It just travels with the rotation of Saturn. So there's really no wind here, 300 miles an hour counterclockwise and then clockwise. Here's the vortex up close, 1,240 mile diameter with the outer wall. And here's the inner eye wall. We noticed that when the Voyagers went out there in 1981, and it's still there now. So we know it's lasted 40 years. We have no reason to think it's not going to be a permanent part of Saturn. South polar vortex, same thing, only substantially larger, 5,000 miles across, 330 mile an hour winds. Here you're looking down, this time of year on Saturn, it's not in the sunlight, so we haven't been able to look down in there to see. But that's looking down into the...
How do you decide what's north and south?
We use the Earth as an example, and since the solar system's flat, whatever is the same direction of our north is their north. Generally looking down, if you look down and it's rotating counterclockwise, they consider that north. Until you get to Venus, which goes the wrong way. For every rule, there's 20 exceptions. And another interesting thing about the south polar vortex, infrared view, brighter areas are hotter, much hotter. This is 100 degrees hotter than the equator. Don't know why. Fahrenheit. I converted to Fahrenheit because that's what most people are familiar with. And we don't know why. Every now and then there'll be a band of heat comes around not all the time. So there's a lot there, a lot going on we don't understand. Next we go out to the rings. 251,000 miles to the E ring, to inside the D ring. The odd part about that is anywhere from 35 feet to 6 miles thick. If you took a sheet of paper to use it as an analogy and cut this in a circle, it would be 1,000 times too thick. If you took a sheet of tissue paper and covered a football field, that would be pretty accurate. The thickness to the width. Some of the rings are thicker, some are thinner. We have them all classified, we give them a letter. Generally by A and B have been known since antiquity. C, D, E, F, G in the order we discovered them. As telescopes improved and we sent probes out. That's when the G ring was discovered by the Pioneer spacecraft in the 70s and 80s. And then the Phoebe ring, which we'll get to later, is way out in the parking lot.
And it's still part of the...
Still part of the Saturn's system. Right here you see this little gap, the Cassini division. These are all named, little gaps are named after physicists and astronomers, Colombo, Maxwell, Cassini, Encke, and Keeler. This one, you notice it's wide, but it's not totally dark. There is stuff going on in there. There's a very, very thin rings coming around in the Cassini gap. Part of the reason is because the first moon that we'll get to, Mimas or Mimas, is double the distance of Cassini to the planet. So any spot on Cassini will orbit twice when Mimas orbits once. And that's called a, it'll come to me. Anyway, they're in tune with each other. What that does is make this area unstable. So if we zoom in on the Cassini division, you can see here it's a lot whiter, it's a lot thicker, more opaque. This is more translucent. This is an unstable area for any particles to come in. So as they slowly float in toward Saturn, they reach these gaps, and it's not stable because of Mimas, and it throws them out, either in or out. So they'll either come back out here, or eventually just come all the way down. Huygens, Herschel, Russell, Jeffries, Kuiper, and Laplace, all astronomers. The interesting thing about that is when we sent the Voyager 1 out, it left here in 77, I think. One of the plans was to run it through the Cassini division because we thought it was empty. But we weren't sure enough to risk a spacecraft going through there. And fortunately we didn't, because it would have never made it. Look at this area here. These gaps are real tight. The edges of the rings are crisp. It's because we have moons there, called shepherd moons. They're also called ravioli moons. Pan is in here, keeping this gap clear. Daphnis in this gap. Janus and Epimetheus are co-orbiting moons, and we'll get to them next. And here, Prometheus keeps the F ring tight. Pandora doesn't really shepherd anything, but it helps clear that area there. Janus and Epimetheus are the only example of co-orbiting moons we have. They're very close in their orbits. Janus is bigger, Epimetheus is smaller. Epimetheus is inside the orbit of Janus. By being inside, it's going to go faster. It takes less time to orbit the planet. So as it's coming along, it's going to catch up to Janus. They get close enough, they start tugging on each other. Pulls Epimetheus forward, lags Janus back. Well, when that happens, when your speed changes, your orbit changes. So by slowing down Janus, it drops down. But since Janus is the more massive of the two, Epimetheus goes out quite a bit compared to what little Janus goes down. Now, Janus is ahead, but it's down in a faster orbit, so it's going to take off away, and Epimetheus is going to start lagging back. So when they're done, this is their final positions until Janus goes all the way around in 4 years, and they'll do the same thing in reverse. Janus will pull Epimetheus back down to here. It'll speed Janus up, back up to here, and every 4 years they switch positions. There's nowhere else we've seen that in the solar system.
How big are those compared to
Oh, much, much, much smaller. Yeah, they are really rocks. These, I think Janus is 20 kilometers. So they're just literally little rocks. Most of these rings are particles from dust to maybe a house-sized. I'd say double this room, and those are the larger pieces in the rings. There's also a million what we call moonlets, because what are you going to have for the smallest size of a moon classification? And they go from this down to nothing, where you have to draw the line somewhere. So we just call everything in the rings a moonlet. And we don't count them with the moons. 83 moons, more moons than any other planet, with confirmed orbits. There's others we've found that we haven't observed them enough to confirm their orbit, so we don't classify them, that are not embedded in the rings. Excuse me. Only 13 are larger than 30 miles in diameter. So not many. Only 7 are large enough to collapse into an ellipsoidal shape, roundish. 2 maintain hydrostatic equilibrium. They're a sphere, or as close to a sphere as it's going to get. If it's rotating rapidly, it'll be oblate. But hydrostatic equilibrium means the gravity and the pressure from the core are in equilibrium. Besides that, we have 24, including that, we have 24 regular moons, prograde orbits. They spin the same direction that Saturn rotates. And they're low inclinations to Saturn's equatorial plane. The same way all the planets are pretty much in line with the sun's equator. All the moons, these moons, are pretty much in line with Saturn's equator. And the rings, because they're along the equator also. The irregular moons could be prograde, could be retrograde. High inclinations, way up here like this. A lot of them are captured SSSBs. If you caught that presentation, SSSBs is the official designation of small solar system bodies.
Oh my gosh.
Okay, we're not inventive when we name things. Centaurs, which are small asteroid-sized bodies that orbit between Jupiter and Neptune. And they usually don't last long because they'll get close enough to a planet to get ejected. KBOs, Kuiper Belt objects, pretty much anything beyond Neptune. Pluto is a Kuiper Belt object. Haumea is a Kuiper Belt object. And or collision debris. There's enough going on there, enough chaos, that when they collide and break up, all those individual pieces start orbiting also. So pretty much to scale, Mimas, Enceladus, Tethys, Dione, Rhea, Titan, Titan is the big player here. Iapetus. Iapetus is 2.2 million miles from the center of Saturn. Phoebe, which we'll get to later, is another 6 million miles farther. So way, way out there. The E-ring that we looked at goes through the orbit of Enceladus, or I should say Enceladus is on the inside edge of the E-ring. And when we look at this planet, you'll understand why there's an E-ring. The inside edge is pretty defined. I couldn't find a way to show this, but it just kind of fades away almost to Rhea. So it's a very wide belt, but it gets very sparse. In this area here, there's like 4 or 5 particles per cubic meter. So we would consider it a vacuum. They would consider it very well populated. Mimas or Mimas, 246 mile diameter. It's really a rubble pile. It's not differentiated. There's not a core and a mantle and a crust. It's just everything mushed together. 85% ice, 15% rock. What you have to remember is that these temperatures, water ice is like granite here. It's very hard. You couldn't ice skate on it. I mean, it's like rock is here. Here's the crater Herschel, 81 mile diameter, 6 miles deep. It offset the center of mass away from the crater. So we think what happened is an object large enough hit, pretty much broke it apart, but the gravity brought it all back together. So the center of mass is offset a noticeable amount. I'm not sure the exact figure. Enceladus, this is the one in the E-ring. You look here, here's some craters, here's nothing. That tells us this is a new surface. So that tells us the surface and the moon are dynamic. There's always change. 310 miles across. This is water ice. 99.5% of the electromagnetic radiation that it receives, it sends back out. That's why it's about 50 degrees colder than a lot of the other moons. Maximum surface temperature, maximum, minus 134. Big rocky core. We think there's an ocean and we think there's liquid water under there. Water, ammonia, and sodium chloride, salt. And then this ice crust isn't connected at all to the core. So it's spinning the same way an automatic transmission works. You get the fluid moving and that takes the crust with it, but they're not connected. We think there's possibilities that somewhere in that ocean life could survive. We don't know that it's happening, but theoretically there could be life under the crust in the ocean. On the south pole of Enceladus, there's geysers spewing out water. There's a few ammonia particles, a little bit of salt coming out too, but here you can see it in the E-ring. It's replenishing the E-ring. So it keeps the E-ring from going empty. And that's also why on Mimas you see the edges of the craters are a little brighter. That's not just the sunlight, it's also fresh material coming on Mimas, and that's what's helping to keep it bright and shiny. These, you can see the grooves here. Those are the areas where the water vapor is spewing out. We think it's because it's close enough to Saturn and Saturn is massive enough that it pulls on it. So as this is going around, all these moons are what we call tidally locked. They have one face toward the planet, like our moon does to us. We only see one face of our moon. If you were on Saturn, you would only see one face of these moons. Not to speak of.
Right. The moons are like way far away from Saturn. Are they highly locked also, or do they rotate?
All the ones we're going to look at here are tidally locked.
Well, the ones that are closest.
Yes, all the major moons are.
Okay.
Even when we get out to Iapetus, that's 2 million miles away, it's tidally locked. Tethys, 660 mile diameter, almost all ice, very little rock in there. What little rock is in there is homogeneous, it's throughout the whole planet. There's no core to speak of. Here's Odysseus, the crater, 280 mile diameter, a mile deep. It's not very deep for such a big crater because this is ice. So it's much easier, although it's as hard as rock, it's not as hard as rock is there. So it can rebound from a major impact like this. It can absorb the impact and rebound much easier than rock can. On the other side, Ithaca, Jasma. It's a canyon system. As this came together and froze, when it came together, first the heat would have melded a lot of that ice. And then when it froze, it expanded. And as it expanded, the crust would have, up here also, the crust would have frozen first. And then as it froze into the core, it had to expand, and it just really split the crust apart. Dione, 700 miles across, about half and half. It does have a core, a rocky core, ice around it. We think this one also might have a liquid ocean under the crust, just by the mass and how it behaves. On the following side, is where we see all the fractures. We don't see them on the leading edge, a few down here, but these aren't really that deep. We don't know why it's just on the back side. About 100 feet high, which on a 700-mile planet is... the discoloration here, we'll get to that. We think we know where that's from. This is the trailing edge. This would be the outside, away from the planet, this side over here. Rhea, much larger, 951 miles, mostly ice, 2575, no core, homogeneous interior, all just mixed together. Here's Tirawa crater, and Mamaldi crater is right here. For some reason, craters on Rhea are named after Native American gods. One of these is a Pawnee, and I'm trying to think of who the other one was. But yeah, this one's named after the Pawnee creation god, and this is after somebody else's spider god. On the back side, we have the Splat. Inktomi crater. It's not all that big, but it's new. That's why it's so bright. This is just freshwater ice that hasn't been exposed to enough sunlight to darken. You can also see here some of the crater walls where the ice splatted up against it. Only 29 miles, about a mile deep, not quite. Then we come to Titan. Titan is the big player here. 3,200 mile diameter, second largest moon in the solar system. Titan is larger than Mercury. Not nearly as massive, because this is half ice. Mercury is 99% metal, nickel iron. It's the only moon in our solar system with a dense atmosphere, denser than actually the atmosphere on Pluto, much denser, and stable surface liquid besides Earth. If we look down through the atmosphere, we find lakes. These are methane lakes. Upper atmosphere is almost all nitrogen, a little bit of methane. The closer you get to the surface, the more the methane increases. It has an active methane cycle the way we have a water cycle. It has methane clouds, methane rain, methane lakes, methane rivers. At this temperature, water ice is like rock. Methane is liquid. You could light a match there and nothing would happen because there's no oxygen. We sent the Huygens probe off the Cassini spacecraft, and it landed on the surface of Titan. First time we landed on another moon. It took a photograph of a plane. It's not real clear, it's very hazy. The atmosphere is hazy from the methane, and up here also. These are 6-inch rock, that's about a 4-inch rock. These are water ice rocks. They show some signs of erosion, so we're thinking that at some time or another, this is part of a riverbed or a lake bed. Water and ammonia ice surface, it's mixed. But actually, this means, to me, this is incredible, that we not only went to Saturn, which is 10 times farther from the sun than us, but we sent a probe that landed on one of its moons and survived long enough to take pictures. After Titan is Iapetus, 900 miles, pretty good size. Mostly ice, 20% rock. You see this. This is the interesting part of Iapetus, and it has to do with Phoebe also. Here's the leading hemisphere. This is the part going first around Saturn. This is the part behind. Black, 5% reflectivity, 60% reflectivity. When we first discovered this in the 1700s, we knew something was up because they could only see it half the time. We could see it with our telescopes, and then it would disappear, and then it would come back, and then it would disappear. And ruling out excessive use of alcohol, we figured there's something up with this moon. Well, what we found is Phoebe, who's out there, way out there, is probably a captured centaur. It's smaller, 132 miles, half rock, half ice, very dark. Darker than carbon black, darker than coal. It has about a 2% reflection rate. It also travels in the wrong direction. It's opposite the way all the others. All the others follow Saturn's rotation. Phoebe goes the opposite way. And it's very inclined, 28 degrees, off of flat. So we think it's a captured centaur, just because there's so much ice. If it had less ice, we would think it's a captured asteroid or Kuiper Belt object or trans-Neptunian object. This crater is Jason. All the craters here are named for Jason and the Argonauts.
Wow.
But at one time, we think this was twice this big and round. But it's been battered by so many collisions that this is what's left. Phoebe rotates in the Phoebe ring. This is the artist's representation. The Phoebe ring is only visible in infrared. That's how we discovered it. We thought it should be there, so we took infrared photos, and that's where we found it. 8 million miles from Saturn is the inner edge, 3 million miles across. Most of this is dust, a few microns, half the width of a human hair. So most of it is just dust, a few pieces over a foot, maybe a soccer ball size. Very little above that besides Phoebe itself. This, we think, came from Phoebe, and as it slowly migrates into the planet, it ends up here. Some of it keeps on going, but that's why Iapetus, on its leading hemisphere, is just sweeping up all the dust that comes in from Phoebe. This is a photograph of Cassini, the Cassini took of Saturn, backlit. The sun is on the other side of the planet, which is why this ring looks so pronounced here. And here you can get an idea of the sharper inner edge, but it kind of fades away as you go out. This is the E ring. This is one of my favorite views of Saturn. And the biggest reason is that little dot right there. That's Earth. That's us. They timed it so the Earth would be visible. And I don't know if you recall, that's when they had told everybody to go outside and wave at Saturn. It was one afternoon. They said at 9 o'clock it would take the picture. What they forgot to say is it's 80-minute light travel time. So you had to go out at 20 to 8.
Wow.
And I did, and I waved. So if you look real close, zoom in, you can see me. So thank you. Been a wonderful audience. Any questions?
What keeps those rings from blowing out all over?
Gravity. Oh, what keeps the rings in place, you mean?
Right.
What keeps them flat?
From that 6 mile down to that.
Just gravity. You know, what keeps the moons there? That's their projection, and they will naturally tend toward the equator.
Right.
And just the gravity of spinning around, there's nothing to disrupt them. There's no force pulling them away. And plus they have their mutual gravity, so they're keeping each other in place too.
You said that, you know, a lot of it was a lot of dust and whatnot. It just hangs right there.
Right, because there's nothing to pull it, there's no force to pull it away. Yes? Correct. Stays with the equator. And, you know, you're in a vacuum, and there's nothing is going to move or change its trajectory without an outside force acting on it. So these are stable enough, they slide in and out, especially when they're near a gap, but there's nothing to move them up or down or just have them blow apart.
Now, they appear to have colors in it if you look through the scope.
They appear to have colors, yes and no. Let me get it up here. They mostly have different levels of density, and some of them are opaque, some are more transparent. Different levels of transparency. Like Cassini here, there's not many of them, so you can see through it. The D ring and the B ring are thicker. So it's not that they're bigger particles, there's just more of them. So that's why it looks a brighter white. The Cassini division, looking with that telescope there, you can see Saturn and its rings. You can see this and this with that telescope. So it's very visible. I mean, you need a good night to be able to see the division, but it's definitely there. These divisions and these rings you won't see with a 4.5-inch telescope, but
Has anybody ever observed an asteroid going through the ring?
has anyone observed an asteroid going through the rings? No. We've observed nothing going through the rings. Assumption being if we did, the little gap they made would close right back up. Because it will try to seek equilibrium. And if you have a hole and thicker area around it, that's not stable. So the particles will try to blend back out. No, we've never seen an asteroid hit Saturn either. Because Jupiter's right there with double the mass. I mean, Jupiter's the big boy in the neighborhood, and he brings everything in to him.
The neighborhood, I think, it's really
Anything else? Well, thank you. You've been a very nice audience.